All right. Let's see here. I think it's time to get started. I'll begin with a word of prayer here. Let me get something open before I forget. What is today? Wednesday? Oh, okay, cool. I'll begin with a word of prayer. Dearly Father, we thank you for this day again. I thank you for these students and for the rain. Help us to glorify you what we do and what we do this day, Lord, and just help us to understand your creation a little bit more today, Lord. In your name I pray, Lord Jesus. Amen. So I will try not to cough violently today, but I make no promises. So we're talking about, of course, rotational motion. And so I want to talk a little bit about like the three-dimensional perspective on rotations. We need to make some definitions, basically. So, definition, if mass m is at position r, then omega vector is defined to be r cross v. So this is r cross v. This is the angular velocity with respect to the origin where r is based, right? Like, so notice that if you changed your coordinate system, right? Well, how about this? If you had two different coordinate systems, right, and they were just related by a linear shift, like I take the coordinate system and say I move it from, you know, my laptop right here, right? And I move the origin over here to the, you know, right here, ignoring the, you know, motion of the Earth around the sun and all that stuff, if you believe in that sort of thing. You know, if I was to measure velocity with respect to this coordinate, so this is coordinate system with this origin, or the velocity with respect to the, you know, coordinate system with this origin, the velocity would be the same, right? Because to get from this point to that point, I can just add a fixed vector that goes from here to here, right? So if you take your position and you add that, and then you differentiate it, it's not going to be different, right? Like velocity is invariant with respect to a shift of the origin, as long as that shifting doesn't have some kind of, you know, funny time dependence or something. So already, this is really different. See, because omega is very sensitive to where the origin is, right? If I change the origin, we change omega. So this is angular velocity, and it is different than velocity, at least in that sense. It's not the same kind of quantity as velocity. It's sensitive to shifts in the origin, for one thing. So there you go. That's angular velocity. Now, like, so if I was to, you know, try to picture this for a second, if this is my mass m, right, and here's my origin vector r, right, and you know, we can think about different cases. Like, let's think about if the velocity was, let's see here. Let me try to draw it out of the board. I should make this picture, right? So that means that the velocity is coming at you, all right? So right hand rule, r, right? E, crossed into, I'm going to fall over, crossed into v like this. So in this context, that would put my omega vector like this. Let me attempt another picture here. Suppose you've got motion in like a circle. All right, and that circle is got the z-axis in its center. All right. I want to talk about what's the angular velocity vector for this circular motion. That's really kind of more what's interesting, right? So if I think about the mass being here, or I could think about the mass being there, right? So we'll first start out with this one. So here's the R, right? Now there's two choices. It's going in a circle, right? Is today Seafall?
No.
Okay, okay. Just checking. Just checking. Some of you look different. Let's see here. I don't have my glasses on though. Maybe you're my students, right?
Sure.
Sure?
Yeah, is this Math 315?
Math 315? What is Math 315 actually? Huh. I don't think we have a Math 315. I should make up a Math 315. What should we cover in there? This is an interesting conversation. Okay, shut up. So, so either it's going this way, right? Or it's going that way. So which way do you want it to go? Let's make it go like this way down here and that way back up there, right? So it's going like that. So at this point right here, to the best of my artistry, the velocity would be tangential to the circle, right? So the velocity would be like, oh man, this marker smells like death. Oh, and not in a good way. Oh, man. Well, I mean, haven't you ever smelled barbecue? So R crossed into V. Oh man, I can't. I need a ring. So R, a ring. R crossed into V. Oh, hey, check it out. All right, a ring. Whoa. Right? So the velocity would be something like that, right? So, and then my position vector up from here, across like that. So, man, that's not right. R cross V? Dang. I'm confused, guys. Yeah. What?
Usually isn't, or I know for,
Something is amiss. Just a second. Yeah?
there is the formula V equals R omega.
V equals R omega.
I don't know if that's...
Just a second, guys. Maybe I'm. It could just be as simple as I need to make sure the circles and maybe my intuition just breaks, unless. All right, fine. All right, so R crossed into V. So, good grief. Let me try to put it. Let me put it. Sorry, guys. I'll have trouble drawing 3 dimensions. Let's put it there. All right. We'll put it there. We'll put it right on the edge, on like that way, at least I've got, I have less issues with drawing in perspective there. All right, so at that point, the velocity goes where? Into the board, right? So we draw it like this. There's your velocity. So I do R, right, crossed V, R crossed into V, and so my angular velocity, something like this. It should be perpendicular to both V and to R, right? That's the cross product. It has to be perpendicular to both of the things you're crossing. Now, over here, if I do it at the exact opposite side, like right here, I'm sorry, guys. I know why I'm getting confused. This is more natural to me. I don't have good intuition for this stuff. It's more natural if you think about a circle in a plane. Then this stuff becomes much more easy to kind of track, and it'll match your intuition better. But let me stick with this here. So now the velocity over here is coming out at you, right? So here's a picture of that. So R crossed into V, so like this, all right? So you kind of get this like cone. The angular velocity is changing, but it's always doing what? It's always pointing, right? It's like pointing this way. So it's just kind of like, you know, just it goes around pointing towards the z-axis as you go around it, if you can imagine that. So if I was to calculate it here, goodness gracious, it would be like that. I can't draw it. I can't draw it anywhere else. I'm sorry, guys. I just can't draw these. Excuse me. All right. So there's example 1. There's example 2. Let me do one that's a little bit easier for us to follow. What if we just have motion in a plane, right? You got circular motion in a plane. You put the origin in the plane, right? You have your r vector here, and your velocity vector, you know, tangential, right? You've got an r vector. I guess I was using blue for the r vector. My bad. You got one over here, right? And the velocity vector is like the velocity vectors are supposed to be I guess I should draw it like this, right? I don't know. Whatever. I'll put one over here. Let's get nuts. The velocity vector, I'm going like this. So it would be like this over here, right? All right, now let's calculate the angular velocity for this particular scenario. It should be more natural. All right? So we got r crossed, oh man, well, you have to kind of visualize it in the plane, right? I go r, here's my velocity, r from the center, crossing the v, my thumb straight up, right? It's the cross product of the radial vector and the velocity vector. It has to be perpendicular to the plane, right? Every time. So in all 3 cases, it's like this. Right? So what's this mean? The way to think of it is if your motion is actually in a planar motion, right? If your motion is actually motion in a plane, then the direction of omega hat is simply the axis, the direction of the positive axis around which you're rotating. Do you see that? So like up defines positive. My right hand going this way defines a positive rotation, which we usually refer to as a counterclockwise rotation. Right? But when you think about it in the abstract, right, you just got a point mass somewhere out in space. You take r cross v, that gives you the angular velocity. That is still something we can define, and it's meaningful. All right? It's just not as intuitive, for me at least, as this. Even for something as simple as this, it still kind of takes me a second to kind of, oh, okay. So the angular velocity is changing as you go around the circle, but it's always pointing towards the axis of the rotation, right? In fact, if you were to decompose this radius into like a piece which was parallel to the axis and a piece which is perpendicular to the axis, that might be interesting there. All right, enough about that. So that's omega vector. Once you have omega vector, you can also define the angular velocity. This is going to be angular momentum. I is, LL is well, it's I omega. But in this context, for a single point mass, that's just M. Oh, goodness gracious. Hold on a second, guys. Let me not do it this way. This is the wrong way to do it. Sorry, just give me a second here. So yeah, I should define it this way. I should say L is R cross the momentum. That's what I want to do. All right, because the moment of inertia concerns the radius of rotation, and like that's not quite a natural concept for the three-dimensional. In 3 dimensions, we might, like what's the radius? I mean, I think the radius is probably this, really, for this motion, because this is motion in a circular plane, right? But if we talk about this in 3 dimensions, the distance from the origin isn't naturally the r that you'd like for like mr squared. So to avoid this, we simply say angular momentum of a point mass in 3 dimensions is r cross the momentum, which if you write it in terms of mass and velocity, you've got m r cross v. All right, so there you go. That's the angular momentum of a point mass in 3 dimensions. Now, notice that, let's see here. What is this equal to, though? There's something I could write. What is this equal to? In terms of things on the board? What is r cross v? Yeah?
Quick question, why is it not R cross V? Why is that not R cross V?
I pulled the m out.
But like, why did you put it on after versus other?
Because I can. I mean, what do you want from me? Are you asking like the deeper reasons? Like,
Oh,
the deeper reason is for the equation I'm about to write. I don't know, like you want to write angular formulas for angular momentum is the larger point here. So there's different formulas. The one formula, if you knew the momentum and you know the position, well, position cross momentum is angular momentum. On the other hand, you could write it as mass times position cross the velocity. On the other hand, you could write it as mass times omega, apparently. Yeah? So, all right, great. What can we do with this? Like, who cares? You're like, well, no, don't answer that. Don't answer that. So we have, so let's differentiate this thing, see what we find. That was an attempt at me writing differentiate, so let's do it. dl dt, what is it? So we have d dt of r cross p. I think I've done some of this before, but let's go through it again. Which is what? This is dr dt cross p, plus r cross dp dt. But one of those terms is obviously 0, right? Maybe obviously is too strong a term, depending on where you are in the course. But at some point, this should become obvious to you. This is the velocity cross the mass times the velocity. And the cross product of any vector with itself is 0, right? And the m pulls out. Again, the m is a scalar. We can pull scalars out of a cross product. Yeah? So this is straight up 0. And this, on the other hand, is what? What is dp dt? Well, Newton's second law says that that's equal to the net force that acts on m, right? So this is so important that it gets a name. This is called the torque, right? The torque with respect to the origin with which we're working, the origin at which r is 0, right? This is the torque. So that's a definition. So essentially there's a theorem, right? The theorem is this, which is that dl dt is equal to the torque. Excuse me. Now at the moment, I'm just talking about a single point mass. All right. Any questions? You can jump in. You guys got questions? So I have an example that I worked through this. Like this is true, even when motion is not circular. This is a law of classical mechanics. It's just as true for circular motion as it is for this marker going like that. dl dt is equal to the torque applied to the marker during that motion. All right? The question is, where's the torque coming from? And how do you understand that? Let's see here. So, a little bit more I should tell you here, and I'll show you some examples. But so what this means, if you look at this, it means that the change in the angular momentum for a point mass, right, is the torque times dt. What does this say? Let's think about it. In other words, if you have L at time t2, it's going to be equal to L at time t1 plus the integral from t1 to t2 of the torque at time t dt. Because we can integrate. So if I have motion that's circular, right? Like how do you characterize circular motion in this language we're talking about today? Like, what does it mean for motion to be a rotational motion in a plane? What has to be the case? Let me ask that question. What does rotational motion in plane imply about the angular momentum? L is m r cross v. If the motion is planar, what can you say about r cross v? What's that?
Points up.
Points
Or
up.
away.
Yeah. Up away from the plane. Perpendicular to the plane, right. Yeah, exactly. So that's exactly it. The angular momentum has to be normal to the plane. Right? If the curve is always in the plane, that has to be the same normal direction, right? It could change, like magnitude could change, but the direction has to be the same, right? So in order for this should be like needs to stay in same direction. What would that take for your torque, right? Your torque would have to be in that same direction, that normal direction. All right? So like if you had if you can imagine this, if you had something, going in this plane in a circle, right? As long as the torque is applied in such a way that the torque vector is perpendicular to the plane, fine. It'll just keep twisting around in the plane, right? But if you apply a torque which is not perpendicular to the plane, but it's like twisted, it is going to cause the motion to lift up off the plane. It's going to twist the motion up off the plane or down into the plane, something like that. Because the angular momentum is no longer going to just be perpendicular to the plane in that scenario. So in order to keep motion in a plane, you have to have the torque in the same direction, plus or minus, as the normal to the plane. These things could also be connected to the larger discussion of the Frenet frame, like the TNB stuff, but I won't do that today because it will go badly. Let me show you guys some, did we got what I'm saying so far? We good? So when is angular momentum conserved for a point particle? You need the torque to be 0, right? If the torque is 0, angular momentum is constant, right? Otherwise, it changes. So let me show you a weird example that I typed up over the weekend because I was sick. I was too sick to do anything except for type physics notes, so I typed a lot of notes. All right. Yowzers. Oh no, the double scrolling got me. Just a second, let me see. All right, so this is what we just went through. Here's an example. It's kind of a silly example, but it'll serve our purposes. Let's study how L is equal to, the LDT is equal to torque for projectile motion, right? What's the position as a function of time for projectile motion? Well, we know it. It's R naught plus V naught times T minus 1/2 GT squared in the, let's say, Z hat direction, if we're talking about gravity going in the Z, yeah? So I can write down, I mean, we've studied projectile motion earlier. We already have all the formulas for the motion, right? We got velocity, we got position as a function of time. We know these things. So let's look at them together here. Here's my velocity, my position. So my angular momentum is and I'm going to make things natural. To make things simpler, I'm going to choose my origin for the angular momentum to be R naught itself. So R minus R naught gives me the coordinate with respect to the origin being R naught. All right? So that just makes this calculation a little bit simpler. But I am calculating the angular momentum with respect to R naught as a pivot point, let's say, okay? So with respect to that, R minus R naught is this, and the velocity is that. And, and if you take the cross product of these two, velocity cross itself is 0. So you just have like the velocity cross Z hat or Z hat cross the velocity, right? Those are both the same thing up to a plus or minus sign, and so you get this minus that. They're both like mgt squared, and so I think, I don't know, you get a half of what's there, plus or minus depending on how I write the cross product. Here it is. So as I said, simplifying, we find that the angular momentum is mgt Z hat cross V naught. Oh, I start up there. 1/2 mgt squared Z naught cross V naught. I calculate. That's what it is. And if I differentiate that, it's easy, right? Because like Z hat cross V naught, that's just a constant vector. When you differentiate, it just sits there. So differentiating 1/2 mgt squared just gives me mgt times the vector. Great. So that's what the LDT is. What's the torque? Well, the torque with respect to the origin R naught is R minus R naught cross F. What is the F applied? The only force that's at play here is gravity. There is no other force on the projectile, right? We're ignoring friction, yeah? So there's no air, you know, it's usual nonsense in here. So here's my R minus R naught cross F. Now the force is minus mg Z hat, right? Because we're taking Z to be gravity. And so you take the cross product, Z hat cross Z hat, 0. And you just got your V naught cross your Z hat, and you get mgt Z hat cross V naught, which is exactly what we found for dLdt. So I don't think of this problem in this way ever, except just to show you that the three-dimensional angular momentum applies to motion you might not think of as being rotational. It's a general concept, okay? And here's another example where I'm calculating angular momentum for a point mass with a velocity. We don't really care about that too much. It's just, yeah, okay, great. This one is more fun. Here I have sort of the more natural use of angular momentum, R cross mv. And when you cross R cross v, it's always up. And so like the direction gives you the direction of the rotation axis. And the magnitude, of course, tells you the angular velocity with respect to that rotational motion. That's the meaning of omega. All right. So in this context, L is in fact equal to I omega, which is mr squared omega z hat. But again, I was tempted to write that formula in the arbitrary three-dimensional context. I don't think I should. I think this formula, I omega, like that, mr squared omega z hat, that only is a good formula if you're talking about motion in a circle, where the radius of the circle is clear and known to be r, okay? Okay. Now, so Excuse me. Ay, ay, ay. So, oh, wait a minute. Hold on a second. This lecture brought to you by the math secretary. She gave me these. There's still hope. All right. So, we just did this integration. That's how the angular momentum changes. It responds to the torque. Torque controls the time evolution of the angular momentum. Now, the study of rotational dynamics generally flows from analyzing the equations L vector is equal to I omega vector. Here I is actually a matrix. So the matrix of the so-called inertia tensor. And the torque, again, is dl dt. But this matrix, more generally, is defined by this lovely integral, which has, this is 0 if it's I is not equal to j. It's 1 if I is equal to j. It's called the Kronecker delta. That's the distance squared. That's like x1 squared plus x2 squared plus x3 squared. And this is just the product of like x1 and x2. So if you're using x1, x2, x3 is xyz, this would be either like, xy or xz or yz. Okay, so the inertia tensor is a specific 3x3 tensor, and what it does is it describes the response of a rigid body to rotational motion in different directions around all three different possible directions. So like what we've been doing in this course is studying rotational motion around a specific axis. So we just need one scalar to describe how it twists, how the motion responds in a twist in just one direction. But if you have an actual three-dimensional object, you might wonder, how does it respond to twists in different directions than just the z, right? This is the thing you have to calculate to answer those questions all at once. It's called the inertia tensor. We don't do it in here, obviously, because I'm not a monster, despite the rumors. So again, this is something for junior level mechanics, which I'm sure this is in the junior level mechanics course here. I'm not really sure if it's there or not. Maybe. All right, so here's the main event, conservation of angular momentum. So we talked about conservation of momentum for a system of n particles, right? We worked this out, that the net external force on a system of n particles gives you the time rate change of the net momentum for the system, which is what? The sum of the momentums for all the particles comprising the system. And ultimately we found that the total momentum for the system was the total mass times the velocity of the center of mass, right? P equals mv was still true for n masses thought of collectively as a single mass m, big M, put at the center of mass. This was our result. Something very similar is possible here. So if we have masses 1 through n at positions r1 through rn, we can calculate the angular momentum of the system as a sum of the angular momentums of all of the masses. Obviously that should be a what? Mn, yeah, m sub n. So sorry about that. And of course, if we define the angular momentum of the jth particle as L sub j, this is of course equal to just the sum of the angular momenta for each of the n particles comprising the system. As I was just saying, we found previously that the change in the total momentum for such a system is equal to the total external force applied. So now we want to see if we can generalize that result for angular momentum. I sure hope we can. Let's see how. So suppose that the n masses under consideration act on each other with certain forces like we did before. We call those internal forces, right? Remember? Newton's third law said the internal forces have to come in third law pairs. Which were what? They meant they were equal and opposite, right? There's a little bit more though. If you read the third law, it says they're equal opposite and they're applied on the line which connects the masses. They have to be applied, the third law pairs, they're applied on the line which connects the two masses in that direction. So they're not just equal and opposite any old different which way. They're equal and opposite along the line that connects the two masses, all right? That's going to be important soon. So so the net force on the mth particle is dp di. That's the external force, and there's two pieces, right? The external force on that mass, but also the sum of the other internal forces, right? J not equal to I. You got all those other internal forces. So from this we can easily calculate the angular momentum on the ith particle here. So I have dl di dt is this. Hey, we just did this calculation, right? I'm just doing it again. So that's 0, and you just get Ri cross dpi dt. This should be very familiar. We just did it. It's right here. So, oops. So Ri cross Fi. So what you got? You got dl dt is equal to the torque on the ith particle. This is not surprising because that's just doing what I just did, but for each mass, okay? Okay, so nothing new there. We just went through that. Now, here's what's new is I can, for this particular problem, there's the force on the ith particle has two pieces, right? You've got the external force and the internal forces. So the external force, let's say the cross product of the position with the external force is going to give us what we'll call the external torque on the ith particle. And then this other piece. You could call that the internal torque if you like, but I just leave it like that for this derivation. Now, then what I do is I take these, there are n equations like this, one for each mass, right? Add these up. Add, right? If you take the sum of all n of those vector equations, you get this bad boy down here. So on the left-hand side, you have the sum of dLei dt for all ix1 to n. But by additivity of the derivative, that's simply dl dt, where L is the total momentum of the system. And then you've got the sum of the external torques on the I masses, and then the sum of the internal torques here. And we're going to be able to argue that this goes to 0. So with this going to 0, that's the natural analog. You have dl dt, where L is the total angular momentum of the system, is equal to the net external torque applied to the system. So the dp dt is equal to the net force for a system naturally generalizes to dl dt is equal to the net torque on the system. It's probably what you'd have guessed if I just put some money on it and waited for a few minutes for you guys to give me an answer. Or maybe you already know it from high school. I don't know. So there we go. Pull the time derivative out because it's linear, additive, you know, and there you go. Net torque, net angular momentum, time rate of change, the derivative of the total angular momentum is equal to the total external torque plus this thing, which will show 0. Why it's 0 is actually kind of interesting. And so if you remember in the previous story arc, when we proved that the total momentum is conserved, I did a very similar calculation to this where I said I split the sum I not equal to j into I less than j and j less than I. And then I like relabel them, and I used that the Fij is equal to minus Fji, and it just went to 0. It didn't quite happen here. When I do the same steps, basically, I find my way to this. So I have Ri minus Rj is crossed with the internal force of the, I think this is the ith mass acting on the j. I can't remember which one it is, honestly. I have to go back and read. I'm not sure if this was the force of the ith mass on the jth mass or vice versa. Okay, it doesn't really matter for our current purposes. The point is, that's the internal, that's the third law pair force, right? What's its direction? It has to be directed on the line that connects the masses, right? So what is this? This is the displacement vector between mass I and mass j. That is in the same direction as this force. What's the cross product of a vector in the same direction with another vector in the same direction? It is 0. So we have a sum of 0, but 0, but 0, but 0. So there you go. That's why angular momentum is conserved for a system. You'll forgive me if I don't write all these things out. But there they are. So I said the derivation here for a finite collection of point masses can be extended to a continuous distribution of masses by appropriately replacing sums with integrals. And you'll thank me for not doing that explicitly in these notes or in this class, right? But we are going to assume those things can be done, as we will soon work examples that are based on that concept, okay? So there you go. This is conservation of angular momentum. Now let me get to the point here. So, so thankfully, we don't have to continue with this three-dimensional viewpoint, all right? In fact, I want to get away from it. I don't want to think about rotations three-dimensionally if I can help it. I would much prefer to think about rotations as they're happening in the plane, which means that rotational motion is essentially a one-dimensional problem, right? Where counterclockwise direction things are thought of as positive, and clockwise direction things are thought of as negative, all right? So as long as everything's happening in the plane, we can just adopt a one-dimensional perspective, and that's what we'll do. So, you know, positive change in theta, counterclockwise, negative change in theta, clockwise rather. If omega is positive, that means that you're increasing in the counterclockwise direction. If omega is negative, you're decreasing in the counterclockwise direction, or equivalently, you're increasing in the clockwise direction, right? And likewise for angular acceleration. If it's positive, that means your d omega dt is positive, which means that you're accelerating into the counterclockwise direction, all right? We don't need vectors for any of this because we just use plus or minus to indicate we're going this way, right? Or excuse me, we're going, however you want to look at it, we're going this way for the, you know, or we're going that way. I need to choose which way is up in order to define the positive sense of the rotation, right? And the negative sense. But anyway. So I wrote this very boring page out to just say the obvious here again. So if this is the case, in this context, the torque is equal to, so what's the story here? In this two-dimensional context, we have a mass, we have a radial arm. The mass times the tangential acceleration is equal to the tangential force, right? But notice that the torque on the mass is r crossed f, right? Which is just r, the radius, times the force, the tangential force. So r times tangential force is torque. And so, on the other hand, a sub t, we can also relate to the angular acceleration, right? Because if that's the tangential direction to the acceleration, then the radius times the angular acceleration gives me the tangential acceleration. We talked about this. Well, I hope you watched the video where I talked about this, right? But so, oh, goodness gracious. So here's some pictures. All we need for 2 dimensions, right? To figure out the torque from a force applied in the plane, we do what? If it's directly perpendicular, it's just r times f, right? But if it's at an angle, then we have to do what? We have to, like, you know, calculate r times f times the sine of phi, right? Because sine of phi would give you the part of it which is perpendicular to the twisting, right? Which is the part which actually gives you torque. So, I'm going to stop there with these notes. Write out some things here in time that remains. Goodness gracious. So let's collect our thoughts here. So let's talk about rotational. By the way, this is not in the notes. This is the thing I didn't quite get to. I mean, it's in my old handwritten notes for sure. But I think one of the things that you need to do as a student is to completely capitalize on everything you know already from the previous part of the story, because it all ties together. Everything we did before, we're doing again, almost without exception. So like here, we have theta. Over here, we had x. Or maybe we had y, right? So angle, position. Here we have omega, which is d theta dt, right? Now here we have v, which perhaps is dx dt, if I'm sticking with x for my coordinate for position, right? The context of this chart is, I'm assuming that we're talking about like rotation in some plane. So we're talking about planar motion. All of this pesky 3-dimensional stuff I was just talking about doesn't really come into play because our focus is on a plane. Next up, alpha, d omega dt. So what's that? Over here you've got acceleration, which is what? dv dt, right? If, and this is an important, if, let me underline that 3 times. If a equals to constant, see, you guys have this habit of ignoring this precondition. This is important. If the acceleration is constant, right, then what? Vf squared equals v naught squared plus 2a times the change in x, right? There's other things. What else do you have? You have like Vf equals to what? V naught plus a times t right? If we're assuming basing things at time 0, let's say for the sake of making the formulas as unannoying as possible, what's the position formula? XF equals to what? X naught plus V naught times T plus 1/2 AT squared, right? Now, a lot of times we have these formulas with A equals to what? Like minus G, and we put X equals to Y perhaps. We're talking about vertical motion, right? But every one of these is just based on simple calculus. And every one of those is also true for angle, right? So you likewise got a timeless equation for angle. Omega F squared equals omega naught squared plus 2 alpha change in theta. Omega F equals to omega naught plus alpha t. Theta F is equal to theta naught plus omega naught t plus 1/2 alpha t squared, right? So we have complete analogy between linear kinematics and rotational kinematics. What else is there? Dynamics, right? What's the foundation of dynamics? Well, in the linear case, it's mass. What is the analog for mass for rotations? What's that? Inertia. I. Right? I. So over here, you have F equals to ma, right? Over here, we have what? We have torque is equal to I alpha. Right? Torque is equal to I alpha is the analog of F equals to ma. Here we have P is equal to mv. Over here we have L is equal to I omega, because mass is like inertia. Anything else that we know? If I can continue this. How about this? We have what? Kinetic energy? 1/2 mv squared. What's the rotational kinetic energy?
1/2 I omega squared.
Right. Do you guys see how the analogy is working here? So we take the mass, it becomes I, the V becomes omega. Is there anything else? Conservation of momentum, right? So here we have dP big D dt is equal to the external force, right? Over here, as I've just derived today, dL dt is equal to the external torque. I guess my angle, you'll forgive me for this small detour into three-dimensional stuff, but of course you can drop the vectors. This is still true in the one-dimensional context, yeah? Anything else? Do we know any other formulas? How about the average of the velocity is the velocity of the average? I mean, what I'm saying is, here you have delta x over delta t. You probably have forgotten about this one. So like v naught plus vf divided by 2. That's also true over here. Delta theta over delta t is equal to the initial angular velocity plus the final angular velocity divided by 2. This is a funny formula. It says that the average velocity is equal to the average of the velocities. When is this true? Is this always, what's that? That's right. This assumes constant acceleration. And when can we not assume constant acceleration? That's not a deeply profound question. The answer is when the acceleration is not constant. So what do you do if the acceleration is not constant? If you don't have these lovely, wonderful formulas, what do you do when the acceleration is not constant? What do? You do calculus, which you know how to do. So hooray. So I'm sure there's a fair amount of that in your homework. After all, I picked it out. And I am a creature of certain habits. So I'm sorry today was a little bit spastic. I'm not well, obviously. And and I'm also sick. But so next time I will hopefully do examples. We'll show you how we can use angular momentum to solve problems like, you know, a duck landing on a record player, like what happens, stuff like that, and so forth. So we, in the full treatment of a collision, we can conserve both linear momentum and angular momentum. It all gets conserved. So we'll see some of that. Thanks, guys. Whew.